Hello everyone, and thanks for watching Edupedia World Videos. In this video we will start a new unit and the first topic will be elasticity. A lot of the behavior of solids and liquids can be described if we assume a standard potential energy curve which goes something like this. The potential energy as a function of r, which is the distance between two atoms or two molecules, is generally taken to be like this. So as r approaches 0, the potential energy goes towards infinity. That means those two objects do not want to be at the same position, right? If r is very far apart, that is, those two objects are very far apart, if r is very large, then the potential energy is close to 0, but it is on the negative side and it is decreasing. We know that the force is the negative of the derivative of the potential energy. So here the derivative of the potential energy is positive, so the slope is negative. That means the force is negative. That means the force is towards the center. So if the two objects are very far apart, then they will be attracted to each other. Because they are attracted to each other, the distance between them will decrease, it will decrease until we reach this point. At this point, the slope is 0, that means du by dr is 0, that means the force is 0. So actually what happens is, very far apart these two particles attract each other, and if they are very close together they will repel each other. Because here the slope is negative, that means the force is positive, that means towards the right. So there is a particular sweet spot in the middle when the attractive and the repulsive forces balance and the net force is equal to 0 and the potential energy is minimum. At that point, if we label it as R0, is actually the equilibrium point. So if we have a solid object, most atoms are related to each other in terms of configuration in a way such that the total potential energy is minimum. Now if we squeeze an object or try to extend or compress it, then this R will change for different atoms or different pairs of atoms, and this potential energy will start changing. Due to this, those atoms will start applying forces towards each other and will try to regain their original potential energy value. Keep in mind, this is a dip. So if the object moves either left or right, it will try to come back to its original position. Right? So this is the sort of behavior that enables us to explain a lot of the behavior of what is called elasticity. Elasticity is simply the tendency of a body to regain its original shape. So you know rubber bands are elastic. If you extend rubber bands, they will and you release them, they will quickly go to their original position. So rubber bands are elastic, whereas some clothes maybe not, right? If you extend them, they do not have the tendency to go back to their original shape. So there are three types of elastic quantities. One is perfectly elastic, that means they completely regain the shape. So if you have a piece of rubber string that is, let's say, 1 meter long, and if you extend it by pulling both the sides apart, and you extend it to 10 meters long, and then you let go, if its original length after it snaps back is again 1 meters, then it is a perfectly elastic body because it completely regains its shape. Then there are bodies which are perfectly inelastic. These bodies have no tendency to regain their shape. Say you have a lump of clay. You could mold that lump of clay into any shape you want. If you manipulate it and make it into a disc, it will stay a disc. It will not come back to its original shape. These bodies are also called plastic. This is the generic use of the word plastic and is different from the standard way in which you use the word, which refers to a type of polymer. The third and basically the type of bodies which every realistic body falls into, those bodies are partially elastic. That means they regain their shape, but not completely. Now if you look at it from a strict point of view, no realistic bodies are actually perfectly elastic or perfectly inelastic. Every body is partially elastic. The only difference is the extent to which they tend to regain their shape. Let's look at it a little bit more quantitatively. Let's say I have a certain random generic object. I make a small area delta S. Small because we do not want this area and the forces acting on this point to change significantly with position. So we take a small area and we look at the two parts of the object on each side of the area. So let's say this part is 1, this part is 2. Both these objects, by Newton's third law, will apply an equal and opposite force on each other, right? And that force can be resolved into two components. This is all general, valid for any delta S. The components can be parallel to delta S and perpendicular to delta S, right? These two components. So let's call the component which is parallel to delta S as Ft, tangential force, and the component which is normal to delta S as Fn, right? So there are two particular quantities, tau n. This tau is different from the tau used in torque. Tau n, which is defined as the normal force divided by delta S. Now again you see why delta S needs to be small. If delta S is a large area, this force might change with position. So tau n, which is the normal force divided by that area, is called the normal, or another word for it is longitudinal stress. That means if you take any area, small area within any body, both sides will apply a force on each other. Those forces will be equal and opposite by Newton's third law. I'm so sorry about this. So both the objects so both the objects will apply an equal and opposite force towards each other. That force may or may not be parallel or perpendicular to the surface. In general, it will have two components, one parallel and one perpendicular to the surface, right? So if you take these two components and you divide it by the area, the component of the force normal to the surface divided by the area is called the normal or longitudinal stress. Similarly, tau t, which is the tangential force divided by the area, is called the tangential or shear stress is another word for it, right? Now this stress can be the longitudinal stress can be further decomposed into two parts. One is tensile stress, tensile stress is when the two parts on either side of the surface pull each other apart, and then there is compressive stress, this is when the two parts push each other. So in this case these are pushing each other, so in this case, this particular case, there is compressive stress. Now this is for a flat surface, but you have an extended object, and let's say if you put it inside water, then it will experience forces on every part of it. And in this case we define a third type of stress, which is volume stress. This is the third type after these two. These two are subsets of longitudinal stress. We have normal stress, we have tangential stress, and if there are forces which are acting perpendicular to the surface everywhere. That is the case if you have an object and you have dipped it inside water. You will learn that later in detail in fluid dynamics, but in that case the force is perpendicular to the surface everywhere, and the force on any small area is actually proportional to the area. If you double the area, and the area is kept small enough so that the force is constant, then the magnitude of the force will become double. In that case, we have tau v, which is, if you label this as Fv, the force normal to the surface, this is Fv by A, and this is basically another word for pressure. So pressure is not just an abstract quantity in itself. Pressure is a part of this bigger quantity known as stress, and pressure is the particular stress in that case when you have forces perpendicular to the surface at all points and you have forces on any small area being proportional to that area. So what we are essentially trying to do now is we are trying to quantify elasticity. Elasticity means you push an object and you can change its dimensions. So stress is the quantification of how much you push an object. We need another quantification for how much the dimensions of the object change, and that quantity is called strain. And it is not the same as stress, but there's a particular analogy which you can see easily in stress. So again, let's say we have a rod, or we have some slightly extended object which has a length L, and if we extend it such that its new length becomes L plus delta L. So we would have obviously applied a certain amount of tensile stress, right? Because we are pulling these two objects apart, these two ends apart, and that will result in the length being increased. So we are applying some tensile stress and the length will change. The quantification of the change of length is called strain, right? And strain is again defined and divided into many different categories. First of all, it is longitudinal strain. And longitudinal strain is when the increase in dimension is in the same direction as the stress. So if the stress applied is in these two directions and the dimension increases in this direction, then we have a longitudinal strain in the object. That strain is defined as delta L by L. So that strain is the change in length. If this much is delta L, it is the change in length divided by the original length. Again, longitudinal stress can be divided into two. Longitudinal strain can be divided into two: tensile strain and compressive strain. Tensile strain is when we pull the object, so in that case delta L is greater than 0, and if delta L is less than 0, it is compressive strain. That means we actually push these two ends together such that the length becomes L minus delta L, or L plus delta L if delta L is negative. This is for longitudinal strain, which is seen whenever we apply longitudinal stress. When we apply tangential or shear stress, we will see what is called shear strain, or sometimes it is just called shear as well, and the definition for it is slightly tricky. So let's say I have this square, and in longitudinal strain occurs when you have the force in the same direction as the displacement. In this case, let's say this is an object and I am applying a force like this, where this is the direction of the force and the two forces are not in the same line. So in that case, this would start shifting and this would ultimately end up being a little bit like this, right? Because these two ends, let's say I'm applying two forces here as well, these two ends will move it towards this side and these two ends will move it towards this side. Or if I replace that, tilted that and put it towards the original thing, the new object will be something like this. Let me make it a little bit clearer. Yeah, so if the original object is a square of these dimensions, the new object will be a square, which not a square but something which will be slightly tilted like this. And shear strain is defined as this delta x divided by this length L. So we see that this length L is in this case perpendicular to this delta x, whereas in this case delta L and delta x are in the same direction. And this is also actually tan theta if this angle is theta. Finally, we had volume stress, and analogous to volume stress, we have volume strain. And volume strain is nothing but if you have an object of volume V and the volume later goes to V plus delta V, then the volume strain is delta V by V. And again, it is compressive if delta V is negative, and it is tensile if delta V is positive. Right. So we have seen two particular quantities up till now. We saw stress and we saw strain. Right. Stress is related to how the molecules interact with each other and what are the forces they apply. Strain is related to the geometrical aspects of the body. Another thing to note, strain is a dimensionless quantity. Strain had the formulas of the type delta L by L or delta X by L or delta V by V. So strain is a dimensionless quantity. Stress is not. Stress has the same dimensions as pressure. Now we will move on to the most important theorem in the topic of elasticity, and this theorem was given by a contemporary of Newton who was called Robert Hooke. So it is in his honor called Hooke's law. And this law relates these two quantities. It relates how the molecules push or pull each other and how much the volume or the length or the breadth changes of an object. So Hooke's law states that if the deformation of a body is small, this is important. So let's say the volume would change by maybe maximum 1 or 2%. In that case, the stress in a body is directly proportional to strain. That means the more stress you apply, the more the volume will change or the length will change. If you apply the double amount of stress, then the volume will change by twice as much as it had previously. Right. Now this also has many different forms. The first form is for longitudinal strain. So in that case, the constant of proportionality is called Young's modulus. And Young's modulus is nothing but the longitudinal stress divided by the longitudinal strain. So it is F by A divided by delta L by L, or it is FL by delta L times E. So if we apply a force F on an object of a cross-sectional area A, then the strain induced in it will be delta L by L, which is related to the stress by the Young's modulus. Now since strain is dimensionless, Young's modulus has the same dimensions as that of stress, which is the same as that of pressure. Similarly, you have another thing which is called the shear modulus. And that is nothing but the shear stress divided by the shear strain. Now these moduli which I'll talk about, Young's modulus, shear modulus, bulk modulus, these modulus are properties of a material. So steel has a particular Young's modulus, which will be quite small because which will be quite large because for a particular strain you have to apply a large amount of stress. Rubber will also have a particular Young's modulus that will be much smaller, right? So this is shearing stress by shearing strain, which is simply F by A. This is F tangential by A divided by X by delta X by L, delta X by L. So that will be nothing but FL by delta X A. This is also, there are some other names for it. This is also called modulus of rigidity. Sorry. Modulus of rigidity or torsional modulus. Finally, you have the most important one, which is bulk modulus, and that is delta P by delta V by V, which is volume stress. Volume stress is nothing but the change in pressure by volume strain. But here there is one small trick. We actually apply a minus sign, and the reason for that is if delta P is positive, if you increase the pressure, then the volume has to decrease. There is no exception to this rule. If you increase the pressure on a solid body, the volume will decrease. So in that case, delta P and delta V will have always opposite signs, and we want the bulk modulus to be a positive quantity. So the bulk modulus is minus delta P by dV by V, right? By the way, all these deltas can be replaced by differentials as well if you're talking about an infinitesimal change, right? There is another quantity related to the bulk modulus denoted by K, which is called compressibility, and that is nothing but the inverse of the bulk modulus, and that measures how much the volume will change by a unit change in pressure. So it is nothing but delta V by V divided by delta P. Percentage change in volume divided by the pressure applied. If for a small amount of pressure you get a large change in volume, then the object will be highly compressible, right? Finally, there is one extra quantity, which is, let's say you have a rod and you are pulling these two ends apart such that the length actually increases of the rod. Then often what will happen is, due to the increase of the length, the cross-sectional area will decrease, or the diameter of this cross-section will decrease, and the change in the diameter of the cross-section is related to the change in the length, the longitudinal length, by the formula sigma is equal to minus delta D by D by delta L by L. Delta D is the change in diameter, delta L is the change in length, D was the original diameter, L was the original length, minus because if the length increases, then the diameter has to decrease, and this sigma again is a property of the material, and this sigma is called Poisson's ratio. So Poisson's ratio, bulk modulus, Young modulus, shear modulus, all of these are properties of materials, right? They might depend on temperature and other things, but they do not depend on how much you extend the body, right? Let's look at the potential energy associated with this extension. So let's say you have a rod and the initial length is L and final length is L plus L. So that means it is extended by small l by applying a force F. So let's say at any point the extension is x. X varies from 0 to small l, and let's say extension increases by a further dx. So in that case, W, the differential amount of work done, will be F dx. But we know one thing, we know the Young's modulus will be F by A divided by X by L, because F by A is the longitudinal stress and X by L is the longitudinal strain, which gives me Y is equal to FL by XA, which gives me F is equal to YAX by L. If I substitute this here, that gives me YAX by L dx. This is dW. So the total work done will be the integral from 0 to small l, because the extension initially was 0 and finally the extension was small l, because total length is capital L plus small l. This gives me the work is equal to half YL square A by capital A. This is also the potential energy stored, because the potential energy is the negative of the work done by internal forces, and the internal forces have to balance this external force, because the net force on this is 0, because the object as a whole is not moving anywhere. So this is also the elastic potential energy. It can also be written in another form. The elastic potential can be written as half into L by L into YL by L into AL, right? Because this L and this L will cancel, and this is actually half into stress into strain into volume. Stress is YL by L, strain is L by L, and the volume is AL. So this is a standard result applicable in any case, which is that the potential energy elastic per unit volume is equal to half into stress into strain. Now one final thing that is left in this topic is springs are a special case for this. So when we had a spring and we said that the spring applies a force F is equal to kx, that was another way of saying stress is proportional to the strain, because strain is proportional to x and stress is proportional to x. Stress is proportional to F. So springs are a particular subset of this, and F is equal to kx is also sometimes called Hooke's law. Thank you.